So good morning, ladies and gentlemen. Glad to see you again. Sorry for technical delays. Technicalities are still overwhelming, but we will get through. Very good. I must confess I have not yet released homework. I gave it a thought and I decided that I better release it after this session, which has some sense. Very good. So now we got lecture number 3, we got second quantization, and we will go on with some technicalities, to exercise our fine muscles, fine mathematical muscles. This will be useful for physical problems, of course. Right. Today, all of us will give a presentation. I will start, and we will go on. So, let me have this pen while this works. Let me see. I would like to outline some very general rules with which you can easily crack any computational problem in second quantization formulation. Some of these rules are rather general and are suitable for almost any task. So, rule number 0, as you see, I'm a good programmer, I always start with 0. So, do not panic. You can certainly do this, whatever complex it is. It's not like these funny problems which you could write down simply, but you won't be able to solve it within a century. No, everything can be done. Just don't panic. Second rule, which is also rather general, but it is of ultimate importance in this course. Do not compute zeros. Many answers in this course are zeros. If you look at the equations I list, most of them have 0 on the right hand side. So, and if you would like to compute all zeros, life is too short. So please take care of not computing zeros. Another rule, which is also a bit obvious, it's what we do with actually most things in our hands. Reduce, if we have something which is made of many, many elements, try to reduce this number in one way or another. And there was another rule, let us see, which is more specific for second quantization, for properties of relation operators, something which we have studied on Thursday. What could it be? Who can have a suggestion? What we can do with operators? Creation, annihilation operators in particular. Right? Again, stress, it's always about doing. It's not about memorizing complex answers. It's about simple motions. What we can do with operators. Say it a little bit lower. Multiply, yes, it's a good direction. But there's no rule which gives you a product. But there is another rule, very close one, which can help. Precisely. In this context, we're going to use commutation relations. If we are dealing with bosons, well, and dicommute if you are dealing with fermions. Right. So those are general rules. And let me formulate a problem. I just wonder how would I place rather let's see formula over here. Let me do it by parts. So it's good. First of all, I have a state. I have a quantum state, which is a number state. It's a basis state in box space, which is completely characterized by a long row of occupation numbers. In particular, it could be a vacuum, all occupation numbers are zero, any set of occupation numbers is fine. Right. Next, I have some operators to compute average of some operators. So I don't want to put too little operators. Otherwise, it would be too easy. I don't want to put too many. If you want too many, there's a nice homework problem about this. And I would like to just give a practical exercise, and I will be dealing with bosons. So I will operate with operators. And since I'm lazy today, it's too early in the morning, I will not put heads. Normally I would put heads, but not today. Please excuse me, I'd like to just a bit accelerate with this. But anytime you see B, it's an operator. It's an annihilation operator. B, I would put it like for bosons. On Thursday, we will do very similar problem for fermions. And then applicational aspect will be clear. I just want to put some rather abstract expression to demonstrate the rules. Okay, PK is operator, annihilation operator. Don't forget this index K. This is annihilation in a certain level. Level is a variable K. Right. And now I'd like to actually formulate the problem. I'd like to compute the average over a number state of the following combination of creation and annihilation operators. Let us see. What do we have after K? Normally L. Here we are. If you recall last lecture, you might want to recall that the interaction is expressed in terms of four creation and annihilation operators. So for practical application, that may be a term arising from computing the first order correction in interaction. One of the terms which enter these expressions. So it is very practical task. Right. And this is KLMN are indices. At the moment, they are not fixed. Fine. All right. Let us apply the rules. First, yes, 0. I don't panic again. So please, I convey this feeling to all of you. Next is to figure out how not to compute zeros. It is a little bit creative process, but it's again a bit, it's this kind of creativity we do when dancing. Let me argue as follows. I have some operators acting on a state, and after the action of these operators, I have to come to the same state. Here, let us recognize it. The states here and here are the same. Okay? Fine. Now what do? I annihilate two particles and some levels, and I create two particles in some levels. And if I annihilate something in level A and create something in level B, that's which and A and B are different, that's going to be very different state. Okay? So it will give 0. Does it go well? Fine. But we don't compute zeros. So let us figure out when this expression won't have zeros. One has a chance to deliver non-zero results. That will happen only if each annihilation will be compensated with creation at the same level. Okay? Otherwise, it wouldn't match. Right. And kind of, you might say it's a deep physical sense or just mathematical operation. There are two ways to arrange this. To make it obvious, I will use kind of arrows. I care about n, and I want to find the match. A level where I annihilate particle in level n, and some of these two b's which create has to be n, otherwise it won't match. And I can choose, for instance, this one. Then for the second one, I have no choice but this one. Let me write it in letters rather than in arrows. It means that L equals N and K equals M. Otherwise, it is 0. Another choice, you can figure out it yourself. It's just a different coupling and is coupled to K, M is coupled to L. All right. Have I exhausted the possibilities? All right. Tell me.
You could act all of them on the same level.
Precisely. Good. So in fact, we have three possibilities. These two have more freedom, and there's very restrictive possibility where all K's are, all KLM are the same. So I will put it here. And in order to distinguish these three, I have to add something, all right? Here I would have to add that M, or the same I can say about K and L. And the same here. Good. So we have to go now through all three possibilities. Let us see. What's my problem? My problem is my age, my memory is a bit overfilled and it looks very slow. So I had to reboot my computer. Today we've lost some time. And again, I have to recall the case. The red case. Let us see, I have to say something about K, something about L. What are they? Who remembers? Otherwise, we'll have to do anything anew. I would bet it is like this. Fine. Let me rewrite the expression. Fine. Let us see. Okay. The L. Fine, good. It's already a bit of reduction, but we still have four operators, right? We still have to do something. Can we reduce it? Well, we could compute the matrix elements explicitly, but it is too long of a way. I don't want to do this. So if we cannot reduce it right away, we need to use the last rule. We need to commute. Right. As I look at it, and I have an idea. What idea? Yes?
Can exchange L dagger and K, then you have PK dagger PK.
Right, indeed. If I exchange these two, I got it in the right order. Fortunately, and it's a piece of lag, since L is not K, those things commute. And I will rewrite the same expression after commutation. Now we can reduce. How do we reduce? That's also what appeared in the lectures. That term is just an operator of occupation number in the level L, which means that if it acts on any number state, it will give us a factor. So let me do it in a slow way. So first I work with this, and I left this. And here I say it just gives me a factor acting on this state. Which factor? Has to be occupation number at this particular level. So that's it. This is NL. Right? And what's that supposed to be? Precisely the same rule that gives occupation number in the same number state. Good. Here is the answer. Let me write it here. And put it in the red frame. Fine, now blue guys. Okay, it's gonna be N and L has to be otherwise. Oh, very good. So how would I rewrite this expression? Let's see. These two are just the same, eh? And here, no, sorry. Yeah. Here I have no. Okay, those are in good order. Oops. This is not in a good order. Fine. What do we do? We commute them again. Now I would like to do it 2 times. Again, I want to put bk to this place, and that I can do because those commute. Right. And then it's not yet good order, so I put it further. Okay, I don't want to rewrite it several times. Just, I take it and put it here. It's all about time. What do we have? What do we have? It's again bk, fine. I use the same rules. That gives me NL, that gives me NK. And it gets a bit boring, so we have also third possibility. And if we were to do IQ test, of course, we would say, it's the same answer. No, I don't think so, so we will have to do it separately. But let me put first this answer. All right. Now I want to consider third case. Okay, so K equals L equals M equals M. Right, so I just write it like this. B K dagger. B dagger K. Ooh. Right, that seemed to be easy, but yeah, they're still not in right order. What do I have to do? Commute. Very good. What do I have to commute? All right, I can try to commute this pair of guys. But, okay, let me write for this case commutation relations explicitly. If
82. And the topic is linear transformation of creation and annihilation operators. So sometimes we have a set of creation and annihilation operators which create states, but they are not necessarily good for us in that sense. For example, they have very complicated formalism. So in some sense, it's sometimes good to change the basis. And we can also do that with creation and annihilation. I will go in a minute on how this is done, but think of this as sometimes it is necessary to solve the problem, or it makes your life much easier. So what we're interested in is a different, let's call it D, or different bosonic operator Dn, which which can be write as a sum of some n, L, and K, which are numbers, or can also be which are numbers in the sense here, coming from a set of bosonic operators, BK. And what we want to do is that this dm also fulfills the bosonic commutation relations and commutation rules, which we already used in the earlier lecture. So I will quickly write them here once. What do we have? We have BK dagger is equal to.
I'm sorry, Max, I think I have questions. It is not the homework what Max is doing. This is taken from presentation list. The presentation list, I believe most of you have already looked at. It's just one of the presentations. Sorry for interrupting.
No problem. So these are the bosonic rules, and what we now want is that our new D also fulfills these. And where do we start? And what are the conditions on this matrix L set by these coefficients N and L and K? So how would you start to this problem? Nobody? That? Yes? Yes, very good. We just plug in and try what comes out. And we choose here the commutation rule first of, so we have in total here 3 conditions, one for a different set of operators and 2 for once the gradation operators, the annihilation operators and the gradation operators. So in total we have 3 conditions we want to solve, we want to have to fulfill, and we start now with the first condition involving the term where we have different operators in the commutator. So what we do is plug in the definitions L and K, B, K. Now we want to set in dm dagger. Dm dagger is defined also via this equation. Let's use here a different index. Which one is good? Let's use T. L. Let's write it this way directly. We have B, T dagger and also L, T, and complex conjugate. Is this everyone clear why there is a complex conjugate? Please say yes or no. So otherwise I quickly show it to you because you can show it in 2 steps, but it would be helpful if you know, because it's important that you know this. Otherwise you will have problems understanding the next pages. So can I go forward? Perfect. So due to the linearity of the operators, of the commutators, what I can do, I can just plug out the sums. And just write it. L and K, P, K, and we have here on the other side, we have B, T, dagger, and we have here B, T, and complex conjugate. And now we use again the linearity property of the commutator. We put this on this side out, this on this side. Because they are scalars, it doesn't matter actually. But if you do it in this way, you can actually also use the same proof if these are operators themselves. If they're not commuting with them. So, K, and now we have EK, B, T, dagger, L, T, and right. Now we know what this is. This just follows directly from our commutation rules. L, M, K, L, T, N, and we get here a delta K, T. With this, we can calculate or compute one of the two sums. Just use sum over K, L, and K, L, L, K, and dagger. And we now enforce, because we want in the end that our commutator of our new operators is again fulfilling the bosonic commutation relation. So we want to set, let me make this bright green. So this is a condition we enforce or we require. And we want this to be M and N. So this is the condition. So this is already the end of part A. But now, what kind of matrix fulfills this condition? Does somebody know? What type of special matrices do you actually know? Let's ask in this way. Yes?
Unitary?
Unitary, that's good. Is there another one? Does it fit actually for unitary?
Yeah.
Perfect, 10 points. Yes, so exactly this is the condition of a unitary matrix. And we can just, because this is just in the end the product of two unitary matrix, which needs to be the identity matrix. So in the end, we have found that L is, or needs to be unitary. That's simple. So, but now we have, in the beginning I said we have 3 restrictions, actually 3 requirements. Now we also have to check if there are not further constraints actually on our matrix L, which needs to be fulfilled. And we do this again by plugging in. Luckily, I only have to plug in one of them and show it, because the other condition is always the complex conjugate condition. So again, plugging this in, dagger, M, T, 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 and conjugate. Now, again, pulling out the sums, we are left with M, B, K, dagger, B, T, dagger, and L, T, N, which needs to be 0. So do I need one more step here, or can I already finish? Yes? Exactly. This condition is always fulfilled, because this is through our bosonic relationship always B0. So here we have a check on this condition always. Yes?
Why can you take out the L operators out of the commutation again?
This one here? Yeah, so here we assume that this LKM is just a scalar.
Okay.
And in this sense, you can just pull it out. You can further make it strong or weaker, but in order to make this an operator, you have to say that this does not commute with any of the B and D K operators and the other one. And then you can also do this kind of proof.
Okay.
You're welcome. Okay, this was a warming up exercise, and in problem B, we now look at a little bit of a more general transformation. We now define our dm as the sum of k, l, and k again, dk. But this time we also add not only an annihilation operators to our new annihilation operators, but we also add a term which consists of creation operators. And I can tell you this transformation will be important in the lecture, and it can help you tremendous to solve very complicated sounding problems with relative ease. So we again have our requirements that our new operator dm needs to fulfill the bosonic creation and annihilation relationships. So again, we do the same proof, or just checking what are the requirements on this now matrix L and this matrix M. I will skip a little bit of the longer parts of the computation due to timing. You can do that then at home, because a few of these commutations. They're not complicated. You always need just to use the commutation relationship and then also expand the commutator itself. So we start with the more complicated one, with dm, dt, sorry, dn dagger, which we require to be delta n. Okay, just plugging in. A quick question. Does anyone know here the Einstein's summation formalism, or otherwise asking other way around, is someone not familiar with the Einstein summation formalism? Okay, there are a few. So I will use explicit sums, but don't hang me up if I forgot a sum or some index to sum over. They should be clear from the context.
Actually, when I was a student, I didn't know that is Einstein formalism.
I think there are many people who actually develop this formalism because in the end it's just laziness, but it works out perfectly.
Einstein was the laziest one, right?
Yes. Okay, so we again plug in our two sums, L and K, B, K, plus M, M, K, B, K, dagger. And on the opposite, we plug in B, it's too long, so I go to the next line. B, T, dagger, and here we have L, M, L, T, N. Plus B, T, and here we have M, T, N, also complex conjugate. So this is what we need to work and also to work out. First, what we do is we pull out the sums, and then, because the commutator is linear in each of its arguments, we can also divide this one big commutator into 4 smaller commutators, which are much easier and nicer to handle. So we have sum over K and T, and the first of the terms is L and K, B, K, and B, T, L, T, and dagger, and here also dagger. The second term is L and K again, B, K, but here in the second we take the second part, and this is B, T, and NTN complex conjugate. The third part in our sum is taking here from the first part of the commutator the second term, which is M K B K dagger, and here we take this again, T T N. T L T N. Okay. Again, these m's are only numbers or commutators which commute with everything here, so they can be pulled out very easily. Sorry? You're absolutely right. Yes. And since we now broken it down, we can immediately see which term's gonna be 0. And following a few of, is it the first rule or the second rule is it? Just ignore zeros.
It's the first rule.
First rule, perfect. So, is this term to be 0? No. Oops. Is this term to be 0? Is this term to be 0? Yes, and this one? Perfect. So we finally are able to reduce our results drastically, and we can now just write the remaining parts, L and K. The commutator between BK and BT. This is just delta KT. And here we have our Tn dagger. And here in the last term, we have Mk, the commutator between Bk dagger Bt. What is this? Is it again just a delta function? Yeah? Perfect. We get the minus sign. And now we can do the same. We just use the delta function to eliminate the sum over t. And I'll finally have a sum which follows L and K, L, K, N, again complex conjugate minus M and K, M, K, N, complex conjugate. And this needs to be delta N. And this gives us a condition for this matrix, or for these two matrices. And
Sorry, there was n in one of the m's is n in the last term.
oh, yes. And this we can also write as a matrix equation, which we have matrix L dagger minus a matrix M, the matrix M dagger, which needs to be density matrix. So this is the condition we get, or which needs to be this L and M to fulfill, which is a little bit more complicated than what we previously had, but it's not too bad, to be honest. But now, what is about the second requirement? And in this case, we especially also need to check the second requirement, 2e, which is that dm dn also has to be 0. Because we now mix gradation and annihilation operators with our dm, this is not explicitly given like in the previous case where we do not mix them. And again, plugging everything in. So kt and k plus m k dagger t b t plus n t t dagger. The procedure is exactly the same as follows. Split this up, use the linearity of the arguments of the commutator, and then find out which terms survive and which one not. So I will skip the step by writing these explicitly and then pulling it out. I directly will pull them out, so to save a bit of time. And here L and K, L and T, and we have here the commutator BK and BT. We have L and K and KN. Sorry, that's not true. And T. And here we have the commutator BK and BT dagger. Two more terms with M and K, L, and T with BK dagger BT. And the last term, which is M and K, M, and T, and we have here the two annihilation operators, the iteration operators. So again, we can say this term is definitely B0. This term is definitely B0. And this term here gives us a delta KT, and this term here gives us, again, a minus delta T. So using all this, we can just write the sum again, the remaining sum, and we have the sum over K, L, M, K, and T minus M, N, K, L, and T, which we need to set equal 0. And this is another condition these two matrices need to fulfill. And this is not immediately clear, but you can also write this as a matrix multiplication condition. You can do this as an exercise at home, but you can find out that this condition is identical, that Lm transposed needs to be equal to ML transposed. And this is the second requirement for this. Let me quickly write this up in B for the more general transformation. We need to have that L or transpose minus M, not transpose, the dagger needs to be identity, and we also need that L and transpose needs to be equal to M L transpose. And there's also question C. Do I have a little bit of time? Perfect. Then I just write you quickly the answer. What changes under the if you have instead of bosonic fermionic operators? This is what you can do as an exercise at home. It's not complicated. It's just doing strictly following the commutation rules, and you find out that for fermionic operators, you have that L dagger plus M, complex conjugate, transpose complex conjugate equal identity, and you have that L and transpose needs to be minus N L transpose. And this is the solution for if you use fermionic commutation rules. And thanks for your attention.
Right, so yeah, a little bit out of time, so if you could accelerate a bit, it'd be nice.
I will be very brief. It's okay, Max, to go to the next page?
Sure. Yep. I will say it in the end.
Okay, so I will be very quick and brief. It's a different topic. It's actually a very simple topic that I have. It's a few words about notation. So, why? Well, motivation for this is that although it might seem more of a, boring part of a course, using proper notation, it can help you a lot in advanced quantum mechanics to choose your notation well. It also helps you to do calculations well, to keep better overview. You've seen in Max's story, now gone, that there can be quite a lot of symbols, operators, sub-indices. Now here it was still okay, Max, but things can and will become more complicated when you're dealing with more complicated Hamiltonians later on in the course, and also in the homework, which we will talk about next week, Monday. So, a few words about notation. Maybe trivial, if you all know it, fine, but I will spend only 5 minutes on it because Michael and Julie also want to say a few words, so bear with me. Last week, no, not last week, 2 weeks ago, we already mentioned the importance of using Dirac notation. You're used to it, I'm sure, but let's see how that works out in a few examples. And I'm going to end the 5 minutes with things to come in the homework. Yeah. So the motivation actually comes right at the end. So 2 weeks ago, we mentioned already that we mostly work, occasionally we use wave functions, but most of the course is written down in Dirac notation. Because it's more convenient. So for example, if you have a system of bosons, let me just draw some levels. So these are energy levels, I'll label them 1, 2, up to n-1 and n. And you have bosons, imagine you have bosons occupying these levels. Then typically you would use, can you read it? Yeah, okay. You would use something like this to indicate the wave function, right? Why do you only need one index here? Anyone? Is it sufficient? Yeah, I see people nodding. Why?
You don't have to account for this here.
Yeah, there's only 1 degree of freedom, right? You only have to label, only have to use a label for the level here, for the energy. Now for fermions, you already mentioned it here, I will need 2 labels because now spin also needs to be specified. So for fermions, imagine I have 1, one fermion, then I would use something like this. I need to specify both the energy, index n, and the spin state. Now what do you do if you have more fermions? So let's say we have 2. How do I write down the wave function then? Make a suggestion. There are usually options, yes?
Just N1, N2, sigma 1, sigma 2.
Yeah. Now I'm going to be a little bit precise. So, because you will already understand that 1 and 2 particles we'll look at occasionally, but n particles, that's our default state that we're dealing with. So you need to have a good notation for that. So for example, I will take n1, sigma 1, and then for the first fermion, n2, sigma 2. I will be very happy if you write wave functions like this in the homework. You could also do alternative, which is also fine, and also easy to work with, and you specify the separate Hilbert spaces. So you could say, I'm going to think of this as following. Right? It's the same wave function, but it shows more explicitly the part for the first fermion and then the cross product with the part for the second. That's the way you combine different Hilbert spaces. And then if I go to n fermions, you would get longer and longer wave functions, brackets, n1, sigma 1, all the way up to nn sigma n. And again, you could also express it in this form. Now, why all this? Why all this? Well, typically, and also in the homework problems, you will have a composite system. I'll explain what I mean by that. And your Hamiltonian, which is usually given, describing the system that you're looking at, will consist of 3 parts, typically. There will be a coherent, so Hamiltonian. We'll have a coherent let me call it quantum part. Well, it's all quantum, but okay. So this typically describes the particle that undergoes evolution. So this could be, for example, a qubit or an electron in a quantum dot. Something like this. That's one part of the system you're looking at. Second part is the environment that this particle or system of particles is interacting with. So there is also a part of the Hamiltonian describing the environment. And then the third part is usually the interaction, the Hamiltonian describing the interaction of the coherent part with the environment that enables it to exchange energy with the environment or to exchange particles with the environment, right? So there's also an interaction part. So let's use an example. I will use colors like Max also did. It's nicer. So, example here, for example, you could have a qubit, I already mentioned it, qubit which has a ground state and an excited state, and that will be the coherent part of your Hamiltonian. The environment we often use is the boson bath. You will hear about it in the lectures as well. Typical Hamiltonian for the environment would be something like this, a sum over modes, let's label them by K, and then there will be VK dagger, VK, and I'm summing over the Ks. Right, this is called a boson bath, essentially a bath of harmonic oscillators. And then there can be an interaction, which describes how these two systems can exchange particles or energy. Now, how would you write down the basis states for a system like this, with a Hamiltonian that is a lot more complex than the fermions and bosons from the previous page? Well, you need to label in your notation the states of both the qubit. I take a qubit here as an example, could also be something else, but the coherent part, and also the environment. And you need to specify both so that we know what state the qubit is in and what state the environment is in. So for example, in this case here, a qubit coupled to a boson bath, if you have one qubit, you could have a situation like this. What do you think this means? What state is the system in? This ket there. What does it tell me? Make a guess.
Ground state for both.
Ground state for both. Yes. Agree? I saw another hand there. Yeah? Okay. Yes. So the first label here specifies the state of the qubit. It's in its ground state. The second label specifies the state of the environment. It has 0 modes. This is a 0, not an O. It has 0 modes. Is it the optimal notation? I would say it's not yet complete. Let's change it to make that more explicit. Let's change it into 1. There's 1 mode. There's something I haven't specified yet about the environment, and that is important. There's 1 mode that I know, given this state, but I haven't specified its K value, right? So better is, if you tell me there's 1 mode with K. Now it's complete. Now I know everything about the state of the qubit and the environment. So be very precise. Right? It's a little bit of a boring subject, perhaps, notation, but once you do calculations, and there are many qubits and many modes involved, it becomes very important to label all the Ks and Ls and Qs and the state of all the qubits. So I could also have, for example, excited state, and then vacuum state in the environment. That's another perfectly fine. Again, if you prefer, you can also write this as in terms of the separate Hilbert space. So ground state for the qubit, and then cross product with the mode in the environment. If you have 2 qubits, or n, doesn't matter, you get the idea, then you could write, for example, GE, and let there again be a single mode with wave vector k. This would describe the state of 2 qubits, the first one being in the ground state, second one in the excited state, and it's coupled to an environment where I have a single mode with wave vector k. Okay, I'll stop here. I hope to see nice notation once you start writing your homework.
Oh, okay. All right.
We are continuing.
Yeah, the same set.
Great. So I'll also do a couple of example exercises to get you used on working with creation and annihilation operators. And to be more specific, I was planning to do from the extra problems, extra problem 6 and 7, but probably I will only do extra problem 6. So if you have Brightspace open, you can open that also open next to you if you want.
It's again like Max, if they say problems, they mean representation.
Right. Okay. And what we're asked to do in the first question is to find the commutation between B power n with B dagger. Right. Okay. So what does this give? This gives, of course, n dagger minus B dagger. I will be sloppy sometimes, so please forgive me if I forget ahead sometimes. Yeah? All right. Now, the question is actually what happens. Now, the curious thing actually is we don't know immediately what happens if we try to swap b to the power of n with b dagger, right? Because this term is actually b dagger. We don't know. But what we can do, of course, is try to swap these two with each other. because we know the commutation relation between B and B dagger, right? So this gives, because of a commutation relation with B and B dagger, this gives 1 plus B dagger B. So what happens if we try to swap B dagger with the B to the right? We swap it one place to the right. What we get is that we get B to the n minus 1 plus B dagger B. So you already sort of see every time that you try to swap B dagger one place to the right, you get two terms. You get one term B n to the power n minus 1, and in the second term you get that B dagger has moved one place to the right, to the left. And now you can already sort of see, if you repeat this n times, you get n times B n to the n minus 1, and a second term where this B dagger has moved from the right completely to the left. And this is equal to now we can of course now combine this all. We see that our commutation for Bn with B dagger is equal to n B to the power n minus 1, because these terms just cancel with each other. Is this clear for everybody? I hope so. I hear no answer, so I'll just continue with the second question. Second question asks, for a sufficient smooth function, f, use the answer A to prove that if we have a commutation between f as function B with B dagger, this should give f prime with B. Right. At first this seems a bit difficult, but it gets relatively straightforward if we expand f as a power series in B. So for f we expand right, I can always do that for a sufficient smooth function. And now you sort of see it. We take the commutation of the sum, but that is the same as the sum of a commutation. So we get that B right? And now, of course, we know what this gives us, because that's what we computed in the first sub-question. This, of course, gives right? And we see that if we fill that in, then we get the derivative of our function. Does this make sense to everyone? Is it good to follow? Am I going too fast? I don't hear an answer again, so I hope it's fine. Okay, then I'll move on to the third sub-question. The first sub-question also sort of builds forth on the same subject. In the third question, they ask you to use or answer B to prove that to prove this. So yeah, where to begin? That's a good question. They say you have to use the answer in B, so I guess at some point we have to take a derivative of something. But before I do that, let's write all the exponents on one side. That will simplify a lot more. To some of you, this expression might seem familiar. These exponents with an operator in the exponent, you commonly see them as propagation or time evolution operators. So to some of you, this might be familiar. So what do we do now? Well, we take the derivative with respect to alpha. If we do that on the left hand side, this is relatively simple. This gives us f prime equals alpha, right? And on the right hand side, we get two terms because of the product rule. We get dagger. Sorry. We get two terms because of our product rule. And what you should sort of realize is that B dagger commutes with the exponent of something times B dagger. Does this make sense to everyone? Does everyone sort of feel comfortable with why? Does everybody sort of know why this is? Why those two commute? Yeah? If I don't hear a no, if everyone is comfortable, then I'll just assume that not. So that means that we can switch these two because they commute. I can't switch those two because I have f as a function of b and b dagger, and b dagger don't commute, so I can't switch them. So what follows is if I switch those, I can simplify my expression a bit more. I get commutation of and well, look at that. What's this? Well, I hope you do know.
You have forgotten dagger, the dagger.
Yes. Sorry. My bad.
Fine, better.
Yes, better. Now they do know. So what is this now? This of course is the derivative of f. And we see that if we and with this we've proven that this expression holds, because as we take the derivative of alpha, we get the derivative of the function on both sides. Right? Again, I don't hear anything, so I assume it's all right. I hope it's all right.
They're just desperately tired.
I guess so. They didn't have a break yet,
Yeah.
so I guess that's maybe that's the reason why.
Just go on. There's little time
I'll be
left.
swift with the last time. The last one is a bit more trickier. The last one, they ask you to prove. They ask you to prove that exponent alpha they prove you to do to prove the following identity. And you see sort of what's happening, because B dagger and B don't commute with each other. Whenever you try to split this exponent into two exponents, you get an additional term because B and B dagger don't commute. Right. Yeah, I see a question. Okay. Which one? The left-hand side or the right-hand side, or both? Oh, okay. Okay. But you can also, if you have Brightspace open, you can open that up. But sure, my bad. Alpha dagger that B equals to exponent dagger exponent that B exponent of 2. This better? I hope so. Great. So where was I? Yeah. And they also give this hint where you should consider the operator S, which is minus S. So where and they ask you to derive a differential equation for O of S. But first things first, what does O of S actually tell us? Well, if S is 0, this gives us 1, sure. But the interesting part is when S is equal to 1, because if S is equal to 1, this should give us exponent of alpha beta over 2. Because if you take S is equal to 1, these all are. I guess I've spoken S over here. Sorry. Because if you take S is equal to 1, these are all 1s, and you see that we get the expression above with these exponents multiplied to the other side. Does everyone see this? Is this understandable? Tractable? I guess so. So cool. What do? You take the derivative with respect to s, and you try to get a differential equation for it. Again, because omega of s consists of 3 terms, when you try to differentiate, you get 3 terms because of the product rule. I won't write down all the terms, but what you get, some terms cancel, but what you get is that you can do the differentiation yourself, and you can double check if I didn't make any mistakes. I hope I didn't. But now the question sort of remains: what does this gives us? Sorry. What does this equal to? Well, from B, you know that, and this equals actually. So yeah, the commutation of B with a function of B dagger. And you sort of already have a hunch to what this is equal to. Anybody an idea?
It's minus the complex conjugate of FB and B dagger.
It's minus the complex conjugate. Not entirely. I'll do a short intermezzo then.
I guess you should not really rely on the response. It's negative times, so
No.
it's derivative, right?
It's a derivative. Yeah. It's a derivative. How much time do I actually have left?
-3.
Okay. So I'll, if you have questions, you can come to me, and I can show you why this is. But either way, we get a rewriting things using this identity. We get the following differential equation, which I hope you are able to solve, gives us and we see indeed when s is equal to 1, we have the exponent of alpha beta over 2. So we've proven what we needed to prove. Okay.
Great,
That's it.
thank you, Michael. Perhaps you can make kind of notes of the last exercise, and I will share it with students.
Sure, I
That
can
would
do
be
that.
fair.
And with the last exercise, you mean 7, right?
Yeah, so.
Okay.
So thank you very much for your attention. Thank you, Zoom participants.